Bismillahirrahmanirrahim. Good afternoon for all participants. Welcome to the Rado Institute. For this time, we will try to discuss about the nice concept for this time. We will give the title of our discussion today with the using Bayesian MCMC. MCMC is mean the Markov chain Monte Carlo to the estimate parameters of the generalized inverse power Rado Institute distribution. We have discussed about the model's generalized inverse power Rado Institute distribution. We have discussed the idea how to create this model. Of course, based on the one recent article that published on the international journal, we can find the idea to create the new models, the generalized inverse power Rado Institute distribution, of course. And we have tried to make the comparison with the SAMS model generalized inverse power Rado Institute distribution for the specific the value of the K. Okay, like the 3, 4, 5, and 6. We try to give the R coding, coding programming computers to solve this problem, especially to the estimate parameters when we are using the some data sets. We have success discussed about that. Okay, for the researchers or the student, if want to have the information about the generalized inverse power Rado Institute distribution, please come to www.radoinstitute.com. You can find this in that website, the information about the generalized inverse power Rado Institute distribution concept. Okay, for this time, we will try to using the concept of the Bayesian Markov chain Monte Carlo or MCMC. We will use this technique to estimate the parameter. Bayesian MCMC, it's mean we will try to upgrade the posterior density using the prior density multiplied by the likelihood function. For this case, the likelihood function comes from the generalized inverse power Rado Institute distribution. And the prior density comes from the normal distribution. So it means the posterior density only need the burning. We will burning until the 10,000 times to get the convergence value. Convergence value to the representative of the parameter of this model. It means we are trying to burn 10,000 times to take the fixed parameters. Fixed parameter is mean we will try to find the convergence, the series of the 10,000 parameter. We will try to check the convergence of this parameter, and then we will try take the one's value to representative of the parameter by taking the median of the 10,000 times burning. Okay, we will try to using the R programming to discuss about the Bayesian MCMC concept. Okay, let's open our R. Okay, this is our R. This is data. This is data set. We run our data sets. Okay. This is our data set Z. We check our data. Okay, this is our data. Okay. Okay. After we have the data, we will try to make the R coding for the likelihood function. Likelihood of the generalized inverse power Rado Institute distribution, especially for the K equal to. Okay, you can find in the blue ones. In the blue one is mean the function, the density function of the generalized inverse power Rado Institute distribution for the k equal to 3. New models, new parameter is means beta. Okay, it means the beta in the generalized inverse. T is mean the alpha, and E is mean the theta. Okay, for the theta. So new is mean the beta, T is alpha, and E is theta. So this is coding is the 4 likelihood function. Okay, prod is mean that we try to make the multiple until n, until the number of the data. So we try using the prod. RR is mean the like this one. RR is the density function of the powers generalized inverse power Rado Institute distribution. So we give the some information. For example, this is for the prior of the parameter beta. This is para the prior of the parameter alpha. This one is the prior of the parameter theta. So we use the concept of the posterior density. We will upgrade with the burning until 10,000 times. This is burning until 10,000 times. We use the formula likelihood function multiplied by the prior information. Okay, the prior information. So we burning until the 10,000, of course. This is for the parameter alpha. And this one is model burning density for the alpha parameters. For this one, for the beta parameter, and for this one, for the alpha parameter. Okay, the same way with the parameter of the beta, we try to using the concept of the likelihoods multiplied by the prior. Okay, this prior. This special for the parameter of the alpha. And this one for the parameter theta. So from this formula, we can find the theory. We will burning for the each parameter until the 10,000 thing. Of course, if we run the program, we will have the 10,000 parameter for the beta parameter, 10,000 for the parameter of the alpha, and the 10,000 parameter of the theta. We will find only one value for this parameter. Of course, we will using the median. We will use the median, of course. This one. We will try to using the median nu for the beta, median T for the alpha, and the median E for the theta. Okay, next let's run the program. We run our program. Okay. This running takes just several times, I think, because we are run about the 10,000 times. Of course, the program will running need the maybe around the 5 or 10 minutes. Let our computer to run this program. Maybe we will discuss about some information about the Bayesian Mcmc. Okay, there are the significant difference between the Bayesian Markov chain Monte Carlo and the maximum likelihood when we are trying to using this concept to the estimate the parameter. We know that if we are use the maximum likelihood, of course we are need the very deeply of the mathematics, very deeply mathematics, because we know that in the likelihood concept, in the maximum likelihood concept, we will need the to solve the non-numerics, to solve the non-linear equation. Of course, we will try to solve the sums non-linear equation by using the numerical concept like the Noether-Raphson. So it's mean we will need the very deeply mathematics when we are try to using the maximum likelihood. But when we are try to using Bayesian Markov chain Monte Carlo, we are not important. We are not use the deeply mathematics. Like you see, we only need the simple programming to burning 10,000 for the each parameter. Okay, only need the simple programmings. But of course, we must have the very good the facility like the computers. I think we have we need the good computer to make the running with the very fast. Okay, our running is finished. Now we can check from the trace plot and the posterior density plot. Okay, we try to check here. Okay, you can see from this laptop. Okay, there are the trace plot and the posterior density. Trace plot is mean we have the 10,000 parameter for the parameter 1. This parameter 1 beta is mean, and then this one the parameter 2 alpha. And the parameter omega is mean the theta. Okay, theta is mean the beta, the parameter 1. So you can check the posterior density is mean you can find from the peaks. Okay, for the each plot have the peaks. Okay, for the each plot we have the peaks. For example, for posterior density of the parameter theta. Theta is mean the beta. This peaks is a representative for the parameter of beta. And then for the alpha, okay? From the posterior density plot for the alpha, we have this the representative of the parameter alpha in the peaks of the posterior density. And this one, okay. For to choose the one value from the 10,000 value, or the value from the peaks of the density plot, we will try to using the median, like I said before. Beta, alpha, and theta. Okay, for this one, we run here. Okay, we can type beta parameter 1, alpha parameter 2, and theta parameter 3. This is the parameter produced by the Bayesian MCMC. Of course, if we have the parameter, we will try to check the parameter using the density and density plots. Of course, we will try to using density plots. Okay. Okay. No. Okay, text. What's problem? Okay, Z. Okay. We try from the beginning. We try run from the beginning. Z. Oh yes, Z. Okay, we try to run from here. Okay, we run from here. Okay, we check again. Okay, this is good. Okay. So we have the two plot here. For this one is the density plot. For this one is the cumulative distribution function plot. Okay. From the density plots, we can find the same result with the generalized inverse power Rado institute distribution using the optim we have discussed before. And for this one, we are using the Bayesian MCMC, the same plot. Okay. The green one is a very nice in the capture the histogram. And then the other CDF plot. CDF plot is mean the cumulative plot. Cumulative plot, the gray one is mean the theoretical of the cumulative. Theoretical cumulative, it means we can find by using the formula F equal to I minus 0.5 divide N. I is the short number 1 until the length N. N is the length, the number of the data, the length data. So the green one is the cumulative distribution function by using the formula like in the equation 2. Okay, like in this equation 1. Okay. We have the equation 1. Equation 1, it means the cumulative distribution function. If we are trying to using gx here by the cumulative distribution function of the inverse power Rado Institute distribution, so we will try to find or create the cumulative distribution function of the generalized inverse power Rado Institute distribution. So from these graphs, okay, the green one, it means the cumulative distribution function of the generalized inverse power Rado Institute distribution. And the gray one, it means that the cumulative theoretical we can find by using formula I minus 0.5 divide n. So we can check here. The green one is the the same with the gray one. The green one, it seems is same with the gray one. So it means our model is very, very good model. So it means the parameter that produced by the Bayesian MCMC is a success to using this data set to make the modeling. Okay, I think our discussion today is very nice discussion. We have success to using the concept of the Bayesian MCMC to produce the parameter. Okay, see you again in the next time with the others model created by the Rado Institute. Rado Yendra and Rado Institute, see you again. Assalamualaikum warahmatullahi wabarakatuh.